timers. Now, usually, when you want to create an output signal, we are going to use a delay signal. Delay is not good for programming, because when you put a delay signal, this means the microcontroller has nothing to do in that time. So you delay the whole work of the microcontroller. So it's not a good way to program using delays. Instead, we are going to use timer and counters. Now, we are going to take in consideration the ATmega 164, which is one of the ATmega microcontrollers. This microcontroller has three timers, two 8-bit timers, which is timer 0 and timer 2, and one 16-bit timer, which is timer number 1. Now, usually we know that signals have frequency and time period, and there is an extra thing which is called the duty cycle. Duty cycle is the time high over the total period, or time high plus time low. So time high over time high plus time low, or the total period. So basically, why do we need pulse width modulation? In order to control the speed of a DC motor, one way is to use the pulse width modulation. Another way, if we want to control the servo motors, we use pulse width modulation to do that. Now, the microcontroller is run by one clock. This clock is called the baseline clock signal. If your microcontroller is running at 2 megahertz, this means that all the components inside the system will run at 2 megahertz or a sub-frequency of 2 megahertz, depending on a prescaler defined earlier. Now, let's assume that our microcontroller is running 2 megahertz. This means that if we want to count up, each count will take 0.5 microseconds, which is 1 over 2 megahertz. So if we have 2 megahertz again, and we are using timer 1, timer 1 is counting 16-bit. Timer 1 is counting 16-bit, which is from 0 up to 65,000. From 0 up to 65,000. This means that each count will take 0.5 microsecond, and we need around 32.76 microseconds to count from 0 up to the maximum value. So this is an example to measure the pulse width. So assume that we had a pulse that its rising edge is at 10 hexa and its falling edge is at 114 hexa. What is the size of the pulse? So in this case, we need to count, the counter will start running at 10 and stop at 114. We need to count the difference in these values, which is 260 decimal. Remember, this is the 10 hexa is 16 and the 114 is 256. So the difference is 260. 260 multiplied by 0.5 microseconds will give us 130 microseconds. This is the width of the pulse. Now, these are the timers. Once more, we have two timers running at 8 bits and one timer running at 16 bits. When we say a timer is running at 8 bits, this means this timer will count from 0 up to 255, and a timer running at 16 bits, this timer will count from 0 up to 65,529 counts. Okay, so this is just to give you an idea. So this timer will count up to 65,000. This timer and this timer will count up to 256. This is the basic block diagram of a timer counter. Just let's go in explaining. This is basically the timer counter. Okay, it takes its clock either from an external source, if we want to run it from external source, or from the clock generator with a prescaler, and then we start the counting from here. Now we have three inputs, which is direction. You want to count up or down, you want to clear, or you want to count. This is the signal for counting. This is timer overflow for interrupt. These are output compare registers A and B. Now your counter will count to a value. If you want at a certain value to produce a signal, you put that value in the output compare register A or output compare register B, and you can see here there's an equal value and we get an interrupt signal or an output signal on the pulses. These are physical pins, by the way. This is all output counter 0A, output counter 0B. Now the counter, you can generate 2 signals from each counter while it's counting. We have 2 control and status registers, which are these 2 registers. It's quite simple, but also not that straightforward, okay? Because there are a lot of modes of operation. Now, the clock source for timer 0 is using selecting clock source from 0 to 2. Let me just go forward to that slide over here, this one. So this is timer counter control register B, okay? Timer counter control register B. Timer counter control register B, it has 3 bits which control the prescaler. If you are doing 0, this means you don't want to use the internal clock. If you put 1, you use the internal clock, which is the CPU. If I say it's 2 megahertz, then I'm using 2 megahertz. If I put 0, 1, 0, it's the clock divided by 8. The clock divided by 64. Here is the clock divided by 8 divided by 256. The clock divided by 8, then divided by 256 to give us different values. If we want external clock, T0 and T1, we can use these as falling edge or rising edge. So these are the timer counter clock selectors as we saw over here. Sorry, we are here. Okay, so these are in timer counter control register B. Then we have the wave generation mode. Wave generation mode is a different story which we can control from timer counter register A and B. So let me go again forward over here. These are the timer counter control register mode. So see, this is bit 2, this is bit 0, this is bit 1, all of them cascaded, they give us the 3 bits over here. So the modes of operation are normal, pulse width modulation for phase correct, compare timer clear, fast pulse width modulation, reverse pulse width modulation correct phase, reserved, and fast pulse width modulation. These are the modes of operation which we are going to discuss later on. So these are all built inside the timer counter control registers A and B. Then we have the actual timer counter register, which is TCNT0, which is timer counter register 0. This is incremented or decremented. It will start counting either from 0 up to maximum, which is either 255 or 65,000, or going down low. We have 2 inputs which we can put our values: output compare register A and output compare register B. We can compare these values with the counter and produce a signal like we are going to see later on. Now the modes of operation are these 4 different modes, which I will go in details over here. First is the normal mode. In the normal mode, the timer counter register will count up from 0 to the maximum. Once it reaches the maximum, it will go back down to 0 and start counting up, and at every time it reaches the maximum, it produces a timer overflow signal. Quite straightforward. The next one is timer counter clear timer on compare match, or CTC, clear counter on compare match. Over here, the timer will start counting from 0 up to a certain value which we are going to put in our counter register A, output compare register A or B. If we put a value here and we select this timer, then the timer will count from here, and then once it reaches that value, it will go back down to 0 and start counting once again. This is very useful to generate any signal with any frequency that we want. If we know each pulse, we can generate the signals quite easily. The next one is phase correct pulse width modulation. In phase correct pulse width modulation, unlike the previous two, the previous two here in the normal mode, we are using the timer counter and using the overflow. Here timer counter along with the output compare register A and B, which will give us values which will trigger the output compare register interrupt. Now over here it's a little bit different story, because the timer is not interrupted. Timer counter will count from 0 till top, then 0 till top, then from top to 0, and so on. Now once your timer reaches the value of output compare register A or B, it will give an output signal which is flip the output signal, the right word, okay? It will toggle the output signal. I'm searching for toggle. It will toggle the output signal. So here, once it reaches the value, it will toggle. It will keep counting, going down. Once it reaches the value again, it will toggle. Quite straightforward. So you generate any pulse using this method. Now the next one is fast pulse width modulation. And the fast pulse width modulation, the same idea. We count from 0 till top, from 0 till top. And once we reach the output compare register A or B, we toggle the output. Now what's the difference? Here we count from 0 till, let's say I'm using an 8-bit. I will count from 0 till 256. Then from 256 till 0. So this in turns will give us around 510 counts, the total period here. Over here we will count from 0 up to 256, then from 0 up to 256, and so on. So it's fast pulse width modulation because we count half of the period. That's why you see here in the equation it is 256, and over here in the equation it is 510. Now these are the modes of operation. Now no need to memorize anything. I will upload another video which will explain how to use all of these with an example. In the support material I put around 28 slides which contain examples on using these modes. Okay, so don't worry about this. I will show you exactly all of this, how to use them, but mainly we are going to use the clear match, this mode, which I will explain to you later. Don't worry about this part. Now the timer control registers A and B, as you can see here, I have already explained the source and I have explained the wave generation mode. The compare A1 and A0 A1 and B0 B1 are basically this slide over here. If you choose the mode of operation to be, let's say, pulse width modulation, then you are going to choose either normal, non-pulse width modulation, sorry, normal, toggle, clear, or set. If you can choose pulse width modulation signal, and from there you can choose the compare output mode that you need, and so on. So this part is for A and this part is for B. They are almost identical. Remember, we need to choose the wave generation mode from here, whether you want it normal. If you choose normal, then this means you are going to go here, no pulse width modulation. If you want to choose phase correct pulse width modulation, then you are going to choose the phase correct pulse width modulation from here. If you want to choose fast pulse width modulation, then you are going to work with this table over here. So it depends on which mode you are going to choose. Now remember, once more, for each timer counter you have two outputs. So I have A and B, and this is shown over here in the, where is it? Sorry. Here we have output A and output B. And on the physical pins on the microcontroller itself, we have these two outputs which are A and B. The last registers to talk about are the interrupt registers. So if you want to enable the interrupts, these are the pins to enable the interrupts. To enable the interrupt for B, for A, and for overflow. And these are the pins where you are going to read the interrupts, where the overflow happens, and these things. Now, these are three examples on how we are going to use them. You can read these examples, and further examples are explained inside the supplementary material. And I uploaded also one question from an exam where it's solved, and it's already on SULMS. I will explain all of these in due time. I will go next to the interrupts. Now, what is an interrupt? It's a hardware mechanism that allows some events to temporarily interrupt an ongoing task. The interrupts are serviced using interrupt service routine, or ISR. We are going to call them ISR. Now, the interrupt service routine, generally very small, quick response, no delay or wait in it. Timer 0 can be configured to generate an interrupt every time it counts from 0 to FF or to maximum. So keep in mind, if my counter counts from 0 to FF, then I can do what? I can trigger a interrupt. I can read the interrupt register that's saying it's an overflow, and when I read that overflow, I will use it through the interrupts. Now suppose that a microcontroller is running 16 megahertz with a clock prescaler of 1024. What's a clock prescaler? Which is this one over here. I'm running a clock prescaler of 1024. Now, so I will have the interval is equal to the frequency over the interval multiplied by 256. So the total interval is 16.384 milliseconds. This means this timer will count from 0 up to 256. Okay, this is my maximum count in 16.384 milliseconds. Okay, because the frequency over prescaler will be the frequency. 1 over frequency is time, so we get this part. Now, to use timer 0 as overflow, we are going to use this line, which is ISR timer 0 overflow underscore vector, which is the vector. Then inside it you write your function. Port B is equal to XORed with 1. This means port B XOR port B with 1, meaning that we toggle the bit every time we do it. XORing with 1 will toggle the bit. So we are going to toggle the bit with a frequency of 30 Hertz, which is 16 multiplied by, divided by 124, divided by 256, and this 2, remember, here we are going to toggle, so the interval we are going to toggle at 0.3 and up another 16.3. This is the total period, which is multiplied by 2. That's why we multiplied by 2 here. So we got 30 Hertz frequency. So what we are using here, we are saying that every time this timer overflows, give me a toggle. Every time the timer overflows, give me a toggle. So the timer will count to 256. Then I'm going to get a toggle over here. This toggle will be a time of 16.34 milliseconds. This is the idea of interrupts and timers. So I can use the timers along with interrupts, but I'm going to use the overflow. I'm not going to go into details of timers. Just use the overflow. How many overflows? Calculate how many overflows you need and you can get it. Now, in order to initialize the ISR or the interrupt service routine, you need to write these few lines. You need to say timer 0 configure timer 0 prescaler, timer 0 enabled, then enable global interrupts, and that's it. If you do this, then you write this small 3 lines, you are going to have this output. Again, another example here, we are using timer 0 to generate a toggle of B0 every second, okay, for a clock frequency of 16 megahertz and 256. Now every seconds mean, first of all, I will get the interval for counting from 0 to 256. I will count from 0 to 256 in 16.384 milliseconds. Each 1 second contains 61 of these intervals. So if I want to toggle every 1 second, I need to count 61. So what we are going to do, we are going to initialize our system over here, and then inside ISR we are going to create a static unit 8 counter. Now, why static? Because I want this variable to be a local variable that does not change from whatever happens outside. So we create a static unit 8 counter equal to 0, and we say counter plus plus. If counter is equal to 61, toggle. If not, we go back and wait for another interrupt. So every time the counter in the main program overflows, it will come here, increment the counter. Then is the counter equal to 61? No. Then continue, and we keep counting from 0 to 65, and every time we get an interrupt, we are going to increment until we reach 61. Then we are going to toggle our value. This is mainly the idea of interrupts and timers and counters. I will be again posting another video for you talking about the examples, and we'll be having team meetings after Eid to discuss further, and if you have any problems. Hope to see you all soon. كل عام وانتم بخير. Stay at home, stay safe, ونراكم قريبا إن شاء الله.